Hey, welcome back to Fat Mama Physics. In this video, we are going to talk about Rutherford's scattering experiment. We're going to do one example, a very classic example, which is if an alpha particle is fired directly at a certain nucleus, how close can it get before it approaches to stop? And this is assuming this is a head-on collision. Otherwise, any sort of an offset from a direct collision is going to cause a scattering effect of that alpha particle. So I'm assuming this is fired directly at a nucleus. So this part here is important, okay? So let's begin. Example 1, an alpha particle, which is essentially a helium nucleus. It is fired directly at a nucleus of, looks like lead-207, at a velocity of 8 times 10 to the power of 5 meters per second. What is the closest it can get to the nucleus? Okay, so this question actually gave us the velocity of the alpha particle instead of its kinetic energy, which sometimes appears in the form of MeV. So actually what I'm going to do is I'm going to do a tag-along question in which the second half I am going to show us how to get MeV from the velocity of a alpha particle. So hopefully when you do see MeV, you will be able to convert that into a velocity or a kinetic energy for you to use. When an alpha particle is colliding with a any sort of nucleus, what happens, here I'll draw it out, is this alpha particle is going to approach as close as it can get before it comes to a momentarily stop, in which all of its kinetic energy is going to get converted into electric potential energy at this point, and which this point we're going to see a final velocity of 0 meters per second, or a final kinetic energy of 0. So all of this kinetic energy is going to be equal to the electric potential energy at this spot here, okay? So let's write that down. And for kinetic energy, this is 1/2 mv squared, or actually I'm going to call it mu squared for initial, of the alpha particle. And this is going to be equal to the electric potential energy between an alpha particle and a lead nucleus. So both a lot of positive, so alpha particle is just the helium nucleus, meaning no electrons, and same thing with lead is just the nucleus with neutrons and protons. So you have essentially a positive charge coming in, getting close to another huge chunk of a positive charge, in which this positive charge is going to stop momentarily before it rebounds back from where it came from. So our kinetic electric potential energy is going to be E. I'm going to do lead, which is Pb, which I'll use big Q for that. And then for the alpha particle, I'll write alpha to signify the charge on an alpha particle, which is just 2 protons. And all of this over R, which is the how close it can get, which is the distance of separation between alpha particle at this spot and the lead nucleus. And that's your kinetic, I see you keep saying kinetic, electric potential energy, okay? So what we will do is, let's do a rearrangement of what R is going to be, okay? So R is going to need to come on top, so we're going to have to multiply both sides by R, which gets rid of that. And then all of this stuff, the 1/2 mu squared, is going to go on the bottom. So I'm going to need to multiply both sides by 2, which then gets rid of that. Also need to divide both sides by mu squared, which gets rid of this as well. So finally we get R. This is equal to 2 times K, which is the Coulomb's constant. Big Q for the charge of a lead nucleus, an alpha particle, divided by the mass of the alpha particle. I'll write little alpha here just to say that's alpha, the alpha particle, and U for that initial speed squared, okay? So the Coulomb's constant, we know, we can get that from the data booklet, which is 8.99 times 10 to the power of 9 a bunch of units, which I'm too lazy to name. I'm so sorry. This Q here is going to be that of a lead nucleus, and this is a notation you need to be familiar with, is that the bottom gives you atomic number, the top gives you atomic mass. The atomic number is going to give you the number of protons. So for lead, the number of protons at inside this nucleus is 82. So Q is going to give us 82 protons times the elementary charge, which is 1.6 times 10 to the power of negative 19 coulombs. For the alpha particle is a helium nucleus, which is essentially 2 protons and 2 neutrons. So 2 protons, which is the positive charge, times 1.6 times 10 to the power of negative 19 coulombs again. One other thing we need to know is the mass of the alpha particle. The mass of the alpha particle is essentially 4 unified atomic mass units. So this is for U. So if we go again to your data booklet, U is going to be 1.661 times 10 to the power of negative 27, negative 27 kilograms. So this is going to be a very small number again. Okay. And then last but not least, the U squared is just this thing. This is the initial speed here. So I'm going to plug all of these into our equation, and afterwards it's going to look like this. So that looks very long, and the next thing we need to do is just put it directly into our calculator. I get 1.775 times 10 to the power of negative 11 meters. Rounding off to about 2 significant figures, this is 1.8. Yes, 1.8 times 10 to the power of negative 11 meters. So notice there's a bit of a deviation from the answer, and I think the reason why is us using the unified atomic mass unit. The reason why we want to use the unified atomic mass unit and not the proton or the neutron is because this alpha particle is technically already in a nuclear form. The protons and the neutrons are glued together by the nuclear strong force, in which maybe you might not have learned about this yet, but because of something called the binding energy between the protons and the neutrons, some of this mass from the proton and the neutrons were used for that, for the binding energy. So in fact, the helium nucleus would have less mass than 2 protons and neutrons combined. So this would be the correct way to use the unified atomic mass unit instead of using the mass of protons and mass of neutrons. That would be used for if later in this unit, actually later in topic 7, actually, when you calculate for, or maybe you know this already, when you calculate the mass defect and the binding energy. Okay, so that is it. That is finding the how close it can get. And so I did say I was going to show us how to convert a kinetic energy of this alpha particle to MeV units. So we know that MeV is essentially mega electron volts, and electron volt is essentially a unit of measurement for energy. So 1 electron volt, oopsies, let's erase this part here. 1 electron volt is essentially the amount of work needed to move 1 elementary charge, 1 electron, through the potential difference of 1 volt. So if we take that, it's going to be 1.6, which is the charge of a elementary particle, times 1 volt, which is going to be that itself, 1.6 times 10 to the power negative 19 joules. So to calculate, to see how many EVs there are, electron volts there are in that amount of kinetic energy, first we need to figure out the kinetic energy of this alpha particle, which is 1/2 m alpha particle times the speed squared. This is just 1/2 4 times 1.661 times 10 to the power negative 27. That's the mass, and then the speed is 8 times 10 to the power of 5 meters per second to the power of 2. So this kinetic energy is, I get 2.126 times 10 to the power negative 15 joules. So to figure out how many EVs there are, I'm going to divide this by 1.6 times 10 to the power negative 19 joules per EV to give me the number of EV, which is 13288. So this is essentially 13 kilo electron volts. Okay, so here we can just leave it like that. Okay, so not enough for a mega, but definitely a lot of electron volts. Okay, so there you go. And of course, if you want to find the speed, you would just have to do the opposite. So you would have to convert the electron volts into joules by multiplying by 1.6 times 10 to the power negative 19 joules, and then possibly divided by the mass and multiply by 2, and of course, and then take the square root of the whole thing to give you the speed of your particle. Okay, so there you go. This is an example, a classic example calculation you would have to do for the Rutherford's experiment. Okay, so I thank you for watching, and I wish you good luck. Fat Mama Physics signing out.